Welcome to Mathematical Analysis. Today we are going to explore a beautiful concept called the integral test. If you have ever wondered how we can add up an infinite list of numbers and get a finite result, you are in the right place. We will see how continuous curves can help us solve discrete problems. Let us dive in. Now that we are ready, let us imagine walking down a staircase that goes on forever. Finding the exact volume of all those discrete, blocky steps one by one would be incredibly tedious. But what if we laid a smooth wooden ramp perfectly over the top edges? That smooth ramp is like a continuous mathematical function, while the steps are our infinite series. If the space under the ramp is finite, the concrete for the steps must also be finite. To use this logic mathematically, our function must meet three strict conditions, starting from a positive integer. It must be continuous with no breaks, it must be strictly positive, and it must be decreasing as we move forward. Before we move on, let us see this with a concrete visual. Here, you are looking at a graph where the horizontal axis represents our variable x, and the vertical axis is our function value. The smooth decreasing curve is our continuous function. Notice the shaded rectangles underneath the curve? These represent the discrete terms of our series, forming a right Riemann sum. Because the function is strictly decreasing, the area of these inscribed rectangles is always less than the exact area under the continuous curve. The rectangles sticking out above represent the left Riemann sum. This visual perfectly captures why the total sum of the discrete series is trapped or bounded by the continuous integral. This visual intuition leads us directly to our formal mathematical boundary. The formula you see here traps the exact area under the continuous curve, the integral in the middle, between two discrete sums. The term on the far left represents the rectangles inscribed entirely underneath the curve, starting from the second term. The term on the far right represents rectangles that stick out slightly above the curve, starting from the first term. If we let the upper limit k approach infinity, the integral and the series are forced to behave the exact same way. If the integral evaluates to a finite number, the right sum forces the series to be bounded and converge. If the integral goes to infinity, the left sum forces the series to diverge. Now that we have our formula and conditions, let us put the integral test into practice with a concrete problem. We are asked to determine if the infinite series of n times e raised to the negative n squared converges or diverges. First, we must define a continuous function by replacing the discrete index n with the continuous variable x. This gives us x times e raised to the negative x squared. We can verify this function is positive for x greater than or equal to 1, continuous, and decreasing because the exponential decay overpowers the linear growth. Since all three conditions are met, we set up our improper integral from 1 to infinity. With our improper integral setup, we need a strategy to solve it. We will use a technique called u substitution to make the integration easier. We let u equal x squared. Taking the derivative with respect to x gives us du equals 2x dx, which we can rearrange to see that x dx equals du divided by 2. We substitute this back into our integral, changing our upper limit to t squared to match our new variable. We also pull the constant fraction of 1/2 out to the front. The antiderivative of e to the negative u is simply negative e to the negative u. Let us finish evaluating this integral. We plug in our upper limit of t squared and subtract the result of plugging in our lower limit of 1. Now, we take the limit as t grows infinitely large. As t approaches infinity, e raised to a massive negative number shrinks exactly to 0. The second term is just a constant. This leaves us with 0 plus 1 over 2e, which equals exactly 1 divided by 2e. Because our improper integral evaluates to a finite number, the integral test guarantees that our original infinite series also converges to a finite value. We have successfully solved the problem. Having successfully used the integral test, we can now apply it to one of the most important families of series in mathematics, the general P-series. A P-series is an infinite series where the terms look like 1 divided by n raised to a constant power p. These series show up everywhere in mathematical analysis. Our goal is to find out exactly which values of the power p will cause this series to converge to a finite number and which will cause it to diverge to infinity. To do this, we will once again turn our discrete terms into a continuous function and apply the integral test. Let us set out to prove the convergence behavior of the P-series using the integral test. We start by defining our continuous function as 1 over x to the power of p, which we can also write as x to the negative p. We then set up the improper integral from 1 to infinity. To evaluate this rigorously, we replace the upper limit of infinity with a variable t and take the limit as t approaches infinity. This is the standard mathematical procedure for handling boundaries that do not end. Because the rules of integration change depending on the exponent, we must split our proof into different cases for the value of p. We will first look at what happens when p is strictly greater than 1. For our first case, let us assume the power p is strictly greater than 1. When we integrate x to the negative p, we add 1 to the exponent and divide by that new exponent. Because p is greater than 1, the new exponent, negative p plus 1, is actually a negative number. As we plug in the upper limit t and let it grow to infinity, t raised to a negative power shrinks all the way down to 0. This leaves us with only the lower limit evaluated at 1, which simplifies to the finite number 1 divided by p minus 1. Since the integral is finite, the series converges whenever p is greater than 1. Now we must check the specific case where the power p is exactly equal to 1. In this scenario, our function becomes 1 over x. The antiderivative of 1 over x is the natural logarithm. When we plug in the upper limit t and let it approach infinity, the natural logarithm of infinity also grows to infinity, even if it does so very slowly. Because the integral diverges, the integral test tells us the series also diverges. If p is less than 1, the exponent becomes positive and it also diverges to infinity. Therefore, we have proven our final result. A p-series converges if and only if the power p is strictly greater than 1. So we have proven how to test if a series converges. This brings us to a highly practical question. In real-world applications, like programming a computer, we cannot actually add up an infinite number of terms. We have to stop eventually. When we stop adding after a specific number of terms, say n terms, we call this a partial sum. Because we stopped early and chopped off the infinite tail of the series, our answer has an error. This error is called the remainder. Fortunately, the integral test provides a brilliant corollary that allows us to estimate exactly how big this error is, ensuring our approximations are safe to use. Let us look at the formula that bounds this error. By integrating the tail end of our continuous function, we can put a strict upper and lower bound on the remainder. Here, the symbol r sub n represents the exact error between the true infinite sum and our finite partial sum. The variable n is the number of terms we actually added together. The formula states that the worst case error, the upper bound, is the integral starting from n to infinity. The best case error, the lower bound, is the integral starting from n plus 1 to infinity. If we increase n, meaning we add more terms, these integrals get smaller and our error decreases. Now that we have our error formula, let us look at a highly practical problem. Suppose we are calculating the sum of the series 1 over n cubed. We want to know how many terms n we must add together to guarantee that our error is less than or equal to 0.005. Our strategy is to use the upper bound of the remainder estimate. We know the error is always less than or equal to the integral of x to the negative 3 from n to infinity. If we force that integral to be less than or equal to 0.005, we guarantee our error is also within that limit. Let us solve this inequality. The antiderivative of x to the negative 3 is negative 1 over 2 x squared. When we evaluate this from n to infinity, the upper limit goes to 0, leaving us with positive 1 over 2 n squared. We set this less than or equal to 0.005. Multiplying both sides by n squared and dividing by 0.005 gives us n squared must be greater than or equal to 100. Taking the square root, we find that n must be at least 10. This means adding just the first 10 terms guarantees our answer is within the required precision. We have covered a lot of ground today, so let us summarize the most important ideas. First, the integral test allows us to determine the convergence of a positive decreasing series by evaluating the improper integral of its continuous counterpart. Second, we used this test to prove that a p-series converges if and only if the power p is strictly greater than 1. Finally, we saw how the tail end of that integral provides a precise mathematical bound on the error when approximating an infinite sum. You now have a powerful set of tools to bridge discrete mathematics and continuous calculus. Great job following along.